Welcome back to the video series. This is section 13.5, graphs of the other trigonometric functions. Today we will be looking at the graphs of tangent, cotangent, secant, and cosecant and their related functions. So I'm going to be switching back and forth between this presentation, and you're going to see stuff on Desmos, and then you'll be able to kind of see how the graphs look. So to graph these functions, these are tangent, cotangent, secant, cosecant, because you guys are experts at graphing sine and cosine now. First of all, you must know where each of them is undefined. And so to know that, you have to know where the denominator of each one is 0. So since all of these functions are functions of sine and cosine, they're going to be undefined when the function in the denominator is 0. So tangent is sine over cosine. So it'll be undefined where cosine is 0. Cotangent is cosine over sine, so it will be undefined where sine is 0. Secant will be undefined where cosine is 0, and cosecant will be undefined where sine is 0. So when you graph them, you're going to see asymptotes where the functions are undefined. If you don't remember what asymptotes are, it's basically when a line approaches another line but never actually touches it. So for cosecant, secant, they're going to be reciprocals of sine or cosine. So if you're trying to graph cosecant and secant, it'll probably be helpful to actually graph the corresponding sine and cosine first, and then use that as a base to graph the other function. So let's explore the fact that tangent is an odd function. So if you remember, tangent of x is defined as sine of x over cosine of x. So is sine of x odd or even? Well, if you remember from what we did before, the sine of x is odd, which means the sine of negative x equals negative sine x. Likewise, the question of cosine of x being odd or even, cosine of x is even, because if you remember, the cosine of negative x equals the cosine of x. So now when you put these two together, how do we know that tangent is odd? Well, we know that y equals tan negative x equals sine negative x over cosine negative x. So we're just doing the same thing with tangent that we did with sine and cosine, checking whether it's odd or even by substituting in a negative x where there was an x. So let's work with this thing now. Based on what we did on the last screen, sine of negative x equals negative sine x, cosine of negative x equals cosine of x. So put it all together, tangent of negative x equals negative tangent of x. Therefore, tangent of x is an odd function. So that's how you know. And so you can do the same thing with the other two trigonometric functions that we're going to explore. Cotangent, secant, cosecant. I guess there's three functions. Let's take a look at example 1. Determine whether the secant function is odd, even, or neither. So you're going to do the same thing that we just did with the tangent, but you're going to substitute in a negative x for an x. So if you want to go ahead and try that, go ahead and you can see the answer in a minute. Alright, so secant of x is defined as 1 over cosine of x. Once again, I want to remind you to remember what secant, cosecant, cotangent, and tangent are functions of, sine or cosine. And really, if anything else, you should be able to do those very quickly from memory, because you're going to be seeing them a lot next year and the year after. Alright, so secant of x is 1 over cosine. Now we're going to substitute in negative x for x. So the secant of negative x is equal to 1 over cosine of negative x. So we're going to play with this thing on the right. What does cosine of negative x equal? That's right, cosine of x. So the secant of negative x equals 1 over the cosine of x, which is, amazingly enough, the secant of x. So since the secant of negative x equals the secant of x, secant is an even function. Go to example 2. Determine if the function y equals tan x plus cotangent x is odd, even, or neither. So do the same thing. You're going to have to play with some fractions here to try to get the answer. Alright, so tangent of x is equal to sine of x over cosine of x. Cotangent of x is equal to cosine of x over sine of x. Now, if you didn't get this far, you can stop the video and try to simplify it into one expression and see what you get. So we're going to have a common denominator, which is cosine x sine x, which means you're going to multiply the top and bottom of this fraction by sine of x, you're going to multiply the top and bottom of this fraction by the cosine of x. So the numerator you have sine squared x plus cosine squared x. In the denominator you have cosine x sine x. Now, if you remember, what does sine squared x plus cosine squared x equal? That's right, 1 over cosine x sine x. I'm doing my best Dora the Explorer impression in case you can't tell. Alright, so 1 over cosine x sine x. Now all we've done here is convert tangent x plus cotangent x to this thing with sines and cosines. Now what we can do is plug in negative x here and see what we get. So the f of negative x is equal to 1 over cosine of negative x sine negative x. Now we remember that cosine of negative x is even, so we have a cosine x here. Sine of negative x is odd, so we have a negative sine x here. Now if you compare this expression with this expression, this is the negative of this one, because this would simplify to 1 over negative cosine x sine x. Therefore, tangent x plus cotangent x is an odd function. So now let's explore the period of the tangent function. Now, if you remember, the period of sine and cosine were both 2 pi. So how do we know that the period of tangent is pi? And that's what it is. It's going to be pi. Well, if you look at a unit circle, you know that y equals sine of x plus pi equals negative sine x. In other words, if you move 180 degrees, the sine of your current value is going to be exactly the opposite. Likewise, if you work with cosine, the cosine of x plus pi, or 180 degrees, is going to be the opposite of cosine of x. Alright, here's a website of the interactive unit circle. If you want to play with it, you can Google it. It's at mathisfun.com. Let's take a look at 60 degrees. If you notice that the sine of 60 degrees, it's actually radical 3 over 2, which is about 0.866. The cosine of 60 is 0.5. Tangent is 1.73, which is radical 3. Now, if we go pi distance around, which is the equivalent of 180 degrees, you will see now that the sine has flipped exactly. It's now negative 0.866. Cosine is negative 0.5, but tangent is still the same, because in both the first and third quadrants, tangent is positive because the sines of sine and cosine are the same. Here they're both positive in quadrant 1, they're both negative in quadrant 3. Likewise, if we go to quadrant 2, and let's take a look at 150 degrees, you see that sine is 1/2, cosine is negative 0.866, and tangent is negative. Now, if you go 180 degrees or pi distance away, you again see that sine is the same number but now negative, cosine is the same number but now positive, but tangent is still the same. So, this tells you that because the tangent of the period of tangent is pi, the tangent of x plus pi has to equal the sine of x plus pi over cosine of x plus pi. Alright? So, all we're doing is changing the signs here, now putting it in a form of tangent. So, remember, sine of x plus pi is negative sine x, cosine of x plus pi equals negative cosine x, and we're back to what we started with. Tan of x plus pi is equal to tan x. So just to recap this slide again, if you move along the unit circle halfway around, 180 degrees or pi units, the numerical value of sine or cosine will be exactly the same, but the sign will be opposite. What was negative is now going to be positive. What was positive is now going to be negative. So now you plug that in, these expressions into tangent. Tangent of x plus pi is equal to negative sine x over negative cosine x, which simplifies to tan x. So the period of tan x equals pi. Now, we know that cosine of pi over 2 is 0. We're now looking at the asymptotes of tangent. So there are going to be asymptotes wherever cosine is equal to 0. Pi over 2 is the equivalent of 90 degrees. So as x approaches 0, tangent of x approaches infinity and is going to be undefined at x equals pi over 2. So there's going to be an asymptote wherever tangent is undefined. Wherever cosine is 0, you're going to have an asymptote. Now, if you do that mathematically, cosine is going to be 0 every pi over 2 units away, where k is an odd integer. So what, 1 pi over 2, 3 pi over 2, 5 pi over 2, etc. Wherever cosine is 0, and where k is an odd integer in this scenario, there are going to be asymptotes for tangent at x equals k pi over 2, where k is an odd integer, which means you're going to have a vertical asymptote at x equals pi over 2, 3 pi over 2, negative pi over 2, negative 3 pi over 2, and so on. So now we're going to explore the graph of tangent. And so to do this, I've decided to go to desmos.com, D-E-S-M-O-S, and it might help when you do graphs in this section to change the x-axis to intervals of pi. So we're going to have radians, we're going to use pi for x, and so that changes the settings to make it so that you have pi. Alright, so let's put in cosine of x, and the reason I want to do that is because I want you to be able to see where cosine is 0. So you can see cosine is 0 at pi over 2, at 3 pi over 2. If we moved over, at 5 pi over 2. We're going backwards, negative 1 pi over 2, negative 3 pi over 2. So at these points, you are going to have asymptotes. So for example, if you want to graph the asymptotes first, that's a good idea. So let's put x equals pi over 2, and you see this purple line. We can create another asymptote at x equals 3 pi over 2, and you see that orange vertical line. So you're going to have asymptotes there. Let's put another one at x equals negative pi over 2. So now you have this black asymptote. Remember, this is the original cosine graph. Now, wherever you see this vertical line here, at every odd pi over 2, you are going to have an asymptote. Now to graph it, let's put in y equals tangent of x. And you can see this is tangent. Now what you will notice is wherever there are asymptotes, it's going to go from low to high. So as you get to pi over 2, it's going to approach infinity. And then on the other side of pi over 2, it's going to start at negative infinity, climb up. And at the intervals of pi, 0 pi, 1 pi, 2 pi, you're going to have it intersecting 0, because that's where sine is 0. So I'm going to now put up a graph for y equals sine x. Just to make it confusing, that's the blue one. So wherever sine is 0, tangent is going to be 0 as well. And tangent is 0 whenever there are intervals, multiples of pi. Okay? So let's clear all this. So what you can see is tangent is going to go from low to high. It's going to have a period of 1 pi. So you can see a whole cycle is between pi over 2 and 3 pi over 2. And it's going to hit 0 in the middle. And wherever cosine is 0, pi over 2, 3 pi over 2, you're going to have an asymptote. So notice again, period of pi. It's going to be symmetrical with respect to the origin. So it's an odd function, and it's going to have a period of pi. I mentioned that already. So to recap what we just saw on Desmos, the graph of y equals tan x is odd, has a period of pi, and has asymptotes at odd multiples of pi over 2. So x equals k pi over 2, where k is an odd integer. So pi over 2, 3 pi over 2, negative pi over 2, negative 3 pi over 2, and so on. So the way you would want to draw it is first draw the asymptotes, make sure the curve goes through 0 at multiples of pi, and graph it. You can kind of get the shape that looks like this. Now if you want to plot more specific points, you can. I'm not as concerned about that because you have software that can do it, but I want you to be able to recognize the shape and how it looks, so you can recognize tangent when you see it. Now we're going to explore the graph of cotangent. So we're back to our blank slate at desmos.com, and remember, cotangent is equal to cosine over sine. So let's first graph y equals sine x so you can see where sine is going to be 0. So you can see at negative pi, at 0, at pi, at 2 pi, sine is 0. You are going to have an asymptotes for cotangent whenever sine is 0, because sine is in the denominator of cotangent. Remember, cotangent is cosine over sine. So let's draw a few asymptotes here. Let's start with x equals negative pi. Let's go to x equals 0, x equals pi, and let's do one more, x equals 2 pi. So you can see where these vertical lines are. The first thing you want to do when you graph cotangent is to graph the asymptotes, and the asymptotes are going to be at multiples of pi. Now, if you take a look at this graph, you're going to see that cotangent is going to go in the opposite direction as tangent. So the blue is the cotangent. So whereas tangent went from low to high, hitting 0 in the middle, cotangent is going from high to low, hitting odd intervals of pi over 2 at 0. So negative pi over 2, 1 pi over 2, 3 pi over 2, 5 pi over 2. That's when the cotangent hits 0. So it's going to start very high at the asymptote, come down, curve gently, hit 0, and then curve down again until it reaches the asymptote of pi, never touching pi. On the other side of pi, it starts up high again and repeats. So it is the opposite function of what was tangent. And again, you can try to see where the asymptotes are by looking at sine, where sine is 0, and graphing the asymptotes. Now, it's going to hit 0 where cosine is 0. So here's the green cosine wave. Since cosine's in the numerator, when cosine is 0, cotangent is going to be 0. So at negative pi over 2, pi over 2, 3 pi over 2, 5 pi over 2. The odd multiples of pi over 2. So unlike tangent, cotangent goes from high to low, asymptotes at multiples of pi, and has a period of pi. So to recap on this slide, y equals cotangent of x is odd, has a period of pi, and has asymptotes at x equals k pi, where k is any integer. So 0, negative 1 pi, 1 pi, 2 pi, etc. etc. So first draw the asymptotes. Make sure your curve goes through 0 at odd multiples of k pi over 2, and then graph it high to low. Alright, so here are both cotangent and tangent on the same graph. You will notice where tangent is 0, tangent is the red one, the cotangent is going to have an asymptote because it's the reciprocal. Likewise, where cotangent is 0, tangent is going to have an asymptote because tangent and cotangent are reciprocals. So you can see how they look together. So let's go to example 3. Graph the function y equals cotangent of 2x. So you're welcome to use Desmos to explore this, but before you graph it, let's think about what we're going to have. We have cotangent. So the asymptotes are going to be at originally multiples of pi, but you have this 2 here. Now, if you remember when we were graphing sine or cosine, what does this number directly in front of the x do to the period? Well, here your b value is 2. So to calculate the period of cotangent, since cotangent's period is pi, the period is now going to be pi divided by b. So the period is now pi over 2. So instead of asymptotes at every pi, you're going to have asymptotes at every pi over 2 because you're cutting the period in half. So let's put some asymptotes there. You're going to have an asymptote at 0, pi over 2, pi, negative pi over 2, negative pi. And then you're going to graph it by going down. So you can see this curve is going to hit 0, halfway between 0 and pi over 2, halfway between pi over 2 and pi, and it's going to go from high to low. And this isn't quite the best graph, but if you do it on Desmos, it'll be clearer. So we're back on Desmos. You can see y equals cotangent of x. So now, if you play with the period and do y equals cotangent of x, cotangent of 2x, you will see that originally the period was pi, and now it's been cut in half. So the orange represents a horizontal compression of the original graph. So what used to take pi to do a whole cycle, now you cram it into pi over 2. And that's what the period does. If you want to elongate it, we can do y equals cotangent of 1/2, 1/2 x. And now what used to take pi now takes 2 pi in black. So we can zoom out, you can kind of see how it behaves. Alright, so just like sine and cosine, a coefficient b that's right in front of the x affects the period. But since the cotangent and tangent periods are pi instead of 2 pi, you're going to divide pi by b to get the period of the new function. So now we're going to explore the graph of secant. So remember, secant is the reciprocal of cosine. So let's first put up the graph of cosine in orange. And if you notice, cosine is going to cross 0 at odd multiples of pi over 2. And since secant is the reciprocal of cosine, whenever cosine is 0, you're going to have an asymptote. So let's put up some asymptotes. Let's put one at x equals negative 3 pi over 2. Let's put one at negative pi over 2. Let's put one at pi over 2. And let's put 1 at 3 pi over 2. All right, so you got some vertical asymptotes. So secant is not going to touch these asymptotes. They're going to be infinity or negative infinity. Now, secant's a much easier graph to do because all you have to do is look at the cosine graph and do kind of the inverted opposite. So notice that when cosine is at 1, where cosine of 0 is 1, the reciprocal is going to be 1. At negative 1, the reciprocal of negative 1 is negative 1. So if we graph y equals secant of x, you will see that whenever cosine is negative, secant is also negative, and it just kind of makes this horseshoe-like shape, this parabolic-like shape. And it's the opposite of the cosine function. So here, let's take a look between negative pi over 2 and pi over 2. Since cosine is even, first of all, notice that secant is an even function. And when cosine is 1, secant is 1. And it's going to basically be on the same side of the x-axis. When cosine is positive, secant is going to be positive. When cosine is negative, down here, secant is going to be negative as well. So you can see what secant looks like. It's basically going to be a repeated cycle of a positive big U and a negative upside down big U, and it's going to go on forever. So it's going to match the cosine function in sine, and just it's going to go in the opposite direction. So to recap, the graph of y equals secant of x, that's the one in dark red. The function y equals secant of x is even, just like its reciprocal. Cosine has a period of 2 pi, so it's going to have one part that's going to be a positive u, another part that's a negative u. Has asymptotes at odd multiples of k pi over 2, or odd multiples of pi over 2, where k is an odd integer. Where cosine is plus or minus 1, secant is also going to be plus or minus 1 since they're reciprocal functions. So here cosine is 1, secant is 1, cosine is negative 1, secant is negative 1. So this pink graph is cosine of x. You can see that secant plays off of cosine by being positive when cosine is positive and negative when cosine is negative. So it's just going to be a series of upside down u's. Finally, let's explore the graph of y equals cosecant of x. So since cosecant is the reciprocal of sine, let's first graph sine. There it is. Now, again, you're going to have asymptotes wherever sine is 0. So it's going to be at multiples of pi. So you can see negative pi, 0 pi, 1 pi, 2 pi. Let's zoom out a little bit. All right, so let's put some asymptotes up. I'll just put some at negative 2 pi, negative pi. Let's make one at 0, x equals pi, x equals 2 pi. All right, so we have some asymptotes at multiples of pi. You can go on forever if you want, but there are better things to do in life. So just like secant, wherever sine is positive, cosecant is going to be positive. You're going to see a u there. Wherever sine is negative, between negative pi and 0, you're going to have an upside down u there. So sine's maximum is at 1. So whatever sine is 1, cosecant is going to be 1 as well because they're reciprocals. Wherever cosecant is negative, sine is negative 1, cosecant is also going to be negative 1. So let's put in cosecant of x. And now you can see this graph in orange. The upside down u, where it's negative, the right side up u, where sine is positive. So you can see how cosecant plays off of sine in the same way, in the exact same way that secant plays off of sine. Wherever sine's positive, cosecant's positive. Wherever sine's negative, cosecant is negative. They're asymptotes at multiples of pi. Okay? Now, just like with cosecant, or just like with secant and sine, the period of the function is 2 pi. So you can have an upside down, a right side up u for pi of the period, and then a negative u, negative upside down u, for the other pi of the period, and then it repeats. So the period of secant and cosecant are both 2 pi. So to recap the graph of y equals cosecant of x, again, this is the graph in red, the u-shaped curves. The function is odd, just like sine, has a period of 2 pi and has asymptotes at multiples of pi, where k is an integer. And where sine of x is plus or minus 1, cosine of x will be plus or minus 1, the same sign, since they are reciprocal functions. So you can see the graph of sine in blue to help use as a reference. So wherever sine is positive, cosecant is positive as well. Wherever sine is negative, cosecant is negative. Let's look at example 3b, y equals 2 secant of x. Well, let's start with a review. So y equals cosine of x and y equals secant of x. So remember, whenever cosine is 0, you're going to have an asymptote. So at odd multiples of pi over 2. Now, how does a 2 in front of cosine affect the graph? Now, you remember, the only thing it does here, let's hide this for now, is that for cosine, if you have a number in front of the cosine, you are vertically stretching the graph. So whereas the minimum and maximum were before -1 and 1, the new minimum maximum are -2 and 2. But the period is still 2 pi. You haven't done anything with the period because b value here is still 1. So now instead of using secant to play off of cosine x, we are now going to play it off of cosine of 2x. So let's hide those two and let's put this one up. So this is now our graph. The asymptotes are still at -pi over 2, pi over 2, 3 pi over 2. The asymptotes haven't moved. So the only difference is now the graphs are going to start higher. So notice they still touch at the minimum and the maximum points. But now the curves are a little steeper than they were before. So before it looked like a much rounder U. You can see that. But because of the decreased area, it's a much steeper U. But it still touches cosine at the maximum points and the minimum points. You have upside down U's. The period is still 2 pi. So basically what this 2 does, the number in front, A, it changes the cosine to make it go higher and lower. It doesn't change the period, and the reciprocal secant still touches at the maximum and minimum points. The asymptotes are still the same. To do example 3c, y equals tangent of 2x. So let's start with the graph of y equals tangent of x. And you can see y equals tangent of x goes low to high as asymptotes at odd multiples of -pi over 2 and hits 0 at multiples of pi. So for y equals tangent of 2x, you can see what's going to happen. Because there's a 2 in front of the x, we are going to cut the period in half. So the period used to be pi, now it is pi over 2. So every pi over 2, it's going to repeat. So I'm going to show you some of the asymptotes. The asymptotes were at odd multiples of pi over 2. Now they're going to be at odd multiples of pi over 4. So let's put in x equals pi over 4. There's one asymptote. Let's put another one. X equals 3 pi over 4. Let's go to the negative side. X equals -pi over 4. X equals -3 pi over 4. So it's hard to see because there's a lot of stuff going on the screen. Let me zoom in a little bit. But pi over 4 is now the new asymptote because the original asymptotes were at every odd pi over 2. You just divide each of those in half. So you have an asymptote at -3 pi over 4, at pi over 4, at pi over 4, -pi over 4, pi over 4, 3 pi over 4, and so on. So now you have asymptotes at every odd 3 pi over 4. So the difference between tangent of x and tangent 2x is that the period has been cut in half. The asymptotes are now twice as frequent. Just divide the previous asymptotes in half. So what was pi over 2 is now pi over 4. 3 pi over 2 is now 3 pi over 4, and so on. Finally, if you were to graph y equals c plus a tangent bx, just like we did with the sine and cosine, you would treat it the same way. The c represents the vertical shift. So you could shift the whole thing up or down a certain number of units. We're not going to do too much of this, so don't sweat it if it's a little too overwhelming. A represents a vertical stretching or shrinking. This is more important for sine and cosine because that changes the minimum and maximum points where sine and cosine are. So sine and cosine graph could be higher or lower, or both higher and lower, depending on the value of A. B represents the change in period. So that's more important. That's something that you should be able to figure out. Remember, the period of tangent is pi. The period of cotangent is pi. So to figure out the period of tangent of bx, just take pi divided by b. For secant and cosine, or secant and cosecant, the period is still 2 pi. Do 2 pi over b to get the period. That's it for section 13.5. You'll have a chance to work on problems in class. If you have any questions, please email me at eliao@musd.org. See ya.